to the computer. All right, welcome back. We have one chapter left here, so we're going to continue through that. Today, I'm starting to go through all of the quizzes and using the statistics thing and figure out which questions people got wrong. And those are the things I'm going to start my review on. So those are the things that I think that obviously are the weakest in the class. So we'll carry on with that. But we're going to finish this chapter first. Wednesday's quiz is on chapter 10 only, radicals only. So be prepared to draw some radicals. Okay, so let's continue on with this. So this chapter is all about alcohols and ethers, the reactivity of and what we can do from them. We figured out how to make them in the alkenes chapter, right? We can make different kinds of alcohols. And now we're figuring out what other things we can do with them. And so on this particular one, we were looking at what we called the Williamson ether synthesis, right? So we want to do a substitution reaction on our alkyl halide with a good nucleophile. If you use the good nucleophile of the hydroxide, then that gives you an alcohol. If you use the good nucleophile of a deprotonated alcohol, that's going to give you the ether. And again, this is an SN2 reaction, so nothing really is different about that. But there is a strategy to do this, because if you want to do a good SN2 reaction, you have to be on a primary alkyl halide or an unhindered secondary alkyl halide. Do tertiary alkyl halides undergo SN2 reactions? Very, very poorly, if at all. Okay, they prefer that SN1-E1 competition. Okay, so that's why when we think about how we want to build our ethers, we have to come up with a strategy that tries to use the alkyl halide with the least hindered attack. So if we looked at this right here, this isopropyl, we could cut it here, and that would give us this alkoxide, and it would give us a secondary alkyl halide. It's like, okay, well, that's not too bad. It's not too hindered. They're only methyl groups. So this reaction will probably work, okay? But if we cut it here instead, okay, notice that we're cutting between the smaller branch than the bigger branch here. That gives us a primary alkyl halide, and it gives us a secondary nucleophile, okay? So is this reaction going to go faster or slower than the other reaction on the other side of the page? Plan A. It's going to go slower, right? Because you have, no, it's going to go faster because you have a nucleophile attacking a primary alkyl halide. So this is going to be faster, okay? And if you switched this isopropyl group out for a T-butyl group, it won't go at all, because you won't be able to do the tertiary alkyl halide on this side. If you switched it on this side and went to a T-butyl group with the alkyl halide on there, it's not going to go at all. So all it's going to do is see this as a base and actually eliminate. Okay, so the strategy here when you want to do a Williamson ether synthesis is you always want to remember it's an SN2 reaction, and you want to use the least hindered alkyl halide, and that means you can still use your bases for that. All right, questions on that? Okay. So another reason we really like these ethers in particular is they're very resistant to acids and bases, but we are going to show you how to chop them up if we need to. Okay, so the next thing we're going to learn here is we're going to learn several reagents. So you'll want to write these down in your reaction table. Several reagents used to create alkyl halides from alcohols. Okay, but we just spent all that time creating alcohols, you know, with all these other ways. Why are we going to convert them? Well, let's say you have an alcohol, but you want an alkyl halide. And sometimes it's not easy to get the alkyl halide you want, so you start with an alcohol. So we're going to convert these and show you some of their reactivity. So in the case of our system here, okay, you actually can't convert it just by attacking it with a nucleophile. Okay, if you just attack it with a nucleophile, it's not going to work. Why?
OH is a bad leaving group.
OH is a bad leaving group. This sentence right here is going to be a recurring theme for the rest of the chapter, by the way. OH is a bad leaving group, except in certain cases. You want to make it a better leaving group. So in the case of this, what we're going to do is we're actually going to use acid to promote our alcohol becoming a better leaving group, okay? So that means for primary, secondaries, and tertiary alkyl halides, we can use acids such as HCl, HBr, and HI to create the corresponding alkyl halides, okay? So the idea would be something like, okay, let's just take HBr here, and we're going to probably protonate here and get that to leave, and then they're going to have our bromine attack, giving us our final product. Okay, and again, it gives us water. Nice weak nucleophile. Okay, questions on that? Okay, now it turns out that there is a difference in reactivity based on the type of alcohol you have. Remember, the type of carbons you have are how many carbons are attached to it. And the alcohol is how many carbons are attached to the carbon the alcohol's on. So in this case here, we only have one carbon, so it's our primary alcohol. We have two carbons, our secondary alcohol, and we have three carbons, our tertiary alcohol, okay? But the tertiary alcohol goes faster than the secondary alcohol, and the secondary alcohol goes faster than the primary alcohol. Why?
Form a more stable carbocation.
Not necessarily. If we were going to do an SN1 type reaction, that would be required. But if we're doing an SN2 type reaction, that doesn't help, okay? So as it turns out, we change the mechanism. The primary can't form a carbocation, right? So it has to go SN2, okay? So it has to wait around for that bimolecular interaction to happen. So that takes time, and that's a higher energy level here. In the case of the secondary and tertiary, you've made OH a good leaving group by protonating it, so it leaves as water, making it easy to form that carbocation, and it's easier to form the carbocation in the secondaries and tertiaries, so it changed the mechanism, okay? So that means the slow step is just having the water leave, and then having the halogen come around and find the carbocation is a very fast step, okay? So overall, the rate increases as you go to tertiary, and your mechanism changes. What does that mean to our stereochemistry? If our SN2 reaction, we're going to have inversion of stereocenter, okay? But our SN1, we're going to have a mixture of things from the top and things from the bottom. So you're going to get racemization in your secondaries and tertiaries, but you're going to have inversion of stereocenter for your primaries, okay? So just remember, it's changing mechanisms. So you want to put primaries on one thing in your reaction table and secondaries and tertiaries on another because it changed mechanisms. Okay, so let's see. There's also a reactivity with the halogens, okay? And it turns out the nucleophilicity goes up as we get bigger because of our polarization. It can be polarized. Okay, so that means HI is going to go faster and give us our iodide than HBr. And then HCl is actually kind of poor. In fact, chlorine is such a bad nucleophile, we actually have to add something to the reaction to make it go. Okay, so in this case here, we're going to have to add a Lewis acid catalyst. And in this case, we're going to do zinc dichloride here. Okay, the way it works is zinc is going to help the OH be a better leaving group, okay? So when we have that, we're still going to be doing an SN2 reaction because it's a primary alcohol. We cannot form that carbocation. But what happens is we have a zinc oxygen bond giving us a positive oxygen and our zinc complex here. Now it makes it easier for that zinc complex to leave, and you end up with zinc hydroxide over here, and your halogen can now be a poor nucleophile because now you have a better leaving group, okay? It's still an SN2 reaction. It's still a primary alcohol when you start, but the zinc is helping the reaction go and makes the SN2 reaction happen faster, okay? This is not required for the secondaries and tertiaries because all you need to do is protonate your OH. Okay. So that's one way to do it, okay? So to get iodine, there you could use HI. You have bromine there, you use HBr. To use chlorine, if it's a primary, you have to use zinc chloride. Okay, so you have to add that as a catalyst to the system. If it's a secondary or tertiary, HCl will work just fine. Okay, so that's making those halogens. Let's see. And so again, the zinc additive here was important to make it a better leaving group. So there's another way to make our OH a better leaving group is to turn it into a sulfonyl ester. And so in this case here, we're going to use a reagent here, SOCl2, which is called thionyl chloride. Okay. This works great in the presence of a base. We usually have a base, it's usually pyridine, which is this little compound here. Okay. And it works for primaries and secondaries only because there is a substitution reaction. Okay. So we're going to see that how that's going to be different. So anytime you see SOCl2, you're going to know you're going to end up with a chlorine on that where your alcohol was. So let's look at the mechanism. It's a little bit different from the book, but it's the most accepted mechanism now. So the idea here is we actually use our alcohol as our nucleophile, and it's going to attack the sulfur. Why? Well, we have a double bond and oxygen's more nucleophilic, so we have a partially positive side of this bond, just like on a carbonyl compound. So it's going to attack that double bonded carbon because it's, double bonded sulfur, because it's just like a carbonyl compound, but it's got a sulfur in it, okay? And that's going to generate our intermediate here, right here. So this is our chlorosulfonyl ester. And what happens is our pyridine deprotonates this compound, giving us a neutral species, okay? When this happens, now that the oxygen is not as bound tightly to the carbon as it is to the sulfur, it's more likely to leave with the sulfur. And so all we have to do is have our halogen right here come over and act as a nucleophile. So it's an SN2 and kick out that oxygen. And it turns out then that decomposes immediately, giving us SO2, another equivalent of chlorine, a chloride ion to act as a nucleophile, and our alkyl halide. Okay. So this is a very clean reaction because the byproduct is a gas. It bubbles out of the solution. So you're able to have no byproducts. Like in the case of HBr, your only byproduct is water. So these are very good reactions for this. Okay, so this is another one that has to go on your list, that thionyl chloride reaction for conversions of alcohols to alkyl chlorides. Okay. But let's say you wanted something else. In fact, thionyl chloride is usually only for chlorines because the bromine and the iodine version are not very stable. And so they don't really work very well. So we use that only for doing the chloride. To get to the bromide or the iodide, we have to use a different reagent. Okay. In this case, we're going to use phosphorus tribromide. Okay. One thing we need to know about phosphorus is it really loves oxygen. And if it can extract an oxygen from anywhere, it's going to. And so that's what it's going to do in this case here. So what we're going to see here is we're going to have our alcohol, and it can be a primary or secondary. Tertiary is a little too hindered. And it's going to react to give us our alkyl bromide and a compound with our oxygen bound to our phosphorus. Okay, so let's look at how that works. All right, so this turns out to be a Lewis base. It's phosphorus. It only has 6 electrons in its outer shell. And so our alcohol acts as our nucleophile, okay, and generates a phosphorus oxygen bond with 2 bromides on it. And now we've generated when this kicked out, it generated our nucleophile, and now it can come in and do our SN2 reaction. Remember, primaries and secondaries only, no tertiaries. And that kicks out a phosphorus compound with the oxygen on it, and we get our bromine. So again, we're creating a better leaving group from our oxygen. Hydroxide is a horrible leaving group. All of these change what the leaving group is. HI and HBr, the leaving group is water. The thionyl chloride, the leaving group is a sulfonyl ester that decomposes into SO2 and chloride ion. Okay. So let's look at that. So in review, what we have here is several different ways to create our alkyl halides. So notice that the only way to create iodine is with this iodide reaction. Turns out that if we tried to make this phosphorus triiodide, it actually is not very stable. It just decomposes and turns back to iodide. But So we have one good way to make our iodine, HI. Remember, it's the fastest one anyway, and it does it for primaries, secondaries, and tertiaries. Okay. So then we have lots of ways to do bromine. We can do it with a PBr3 or the HBr and get our primaries and secondaries to make it that way. We have our zinc chloride for our chloride one on primary alcohols, primary and secondary alcohols, because we still need that SN2 reaction. But we can also convert the PBr3 into PCl3 or 5 in some cases, and that will also generate a chloride. And then thionyl chloride will also generate a chloride. So we have 1, 2, 3 ways to create a chloride because HCl by itself didn't work. So they created other reagents around it so that we could do that. But HBr works great, HI works great, and PBr3 and PCl3 will also work well. All right, questions now. Okay, so those are all pretty simple. We're using mechanisms we already know, and we're just using reagents that are making our oxygen a better leaving group. All right, so how else can we make an oxygen better leaving group? We can turn it into a sulfonic acid derivative. Okay, so in this case here, we're going to start with the tosylate group here. And we've actually seen it on a couple of quizzes, maybe this OTS right here. That is a leaving group like an iodine or anything else. It's just really good leaving group. Okay, so the concept here is it's Paratoluene Sulfonate. So this compound here is toluene. It's a methyl group on a benzene ring. And then we have a sulfonic acid on this side here. Okay, that whole group of the sulfur with 3 oxygens and that benzene ring is called the tosylate leaving group, or the tosyl group. Tosyl group right here. Okay. So what we've done here is instead of having our OH as our leaving group, we now have a sulfonic acid. This is leaving as an anion. Okay, sulfonic acid has a pKa of -2. So that means it's a really weak base. So that means it's going to fall off and just be perfectly stable as an anion. It'll be protonated eventually, but so the abbreviation is TS, and that whole group takes off the oxygen. So how do we make this cool group that is having us be able to eliminate our OH again? Well, it turns out we just need to use the chloroderivative of this sulfuric acid. Okay, so this is called a Tosyl Chloride. Okay, and what we do is in the presence of a base, it will come and react with the OH is going to come and attack the sulfur, kicking out the chloride, and we're going to end up getting our group on here. So we can really get lazy and put the TS there. And then it's going to give you a little bit of acid with the pyridine. So you need to use the pyridine in there because it's very important. It's only -2. Okay. So in this case here, we've created that using Tosyl Chloride, or TSCl, and pyridine, and that created a good leaving group. Now, once we have that, we can attack it with any nucleophile. But let's talk about why that anion is just so stable to leave. Okay, the reason it's so stable to leave is it has lots of different possible configurations or resonance contributors. Okay, so we can have that oxygen. Any of the 3 oxygens can carry the negative charge, spreading that charge around, making it again very, very let's see, what's the word? Diffuse, and it has not a charge on one area, making it more stable as the anion, making it a better leaving group. So it's a really good leaving group. So again, we've used sulfur before in our thionyl chloride to make it our oxygen a better leaving group. We've used phosphorus to make our oxygen a leaving group. Now we're using this sulfonic acid to help oxygen become a better leaving group. Okay, so once you have it, you can actually get rid of it in a couple different ways. Most of the time, it's going to be an SN2 reaction or an E2 reaction. Okay, so if we have a good nucleophile, we can actually use it as a good nucleophile and get substitution on it. And so in this case here, we're going to make an ether out of an alcohol right here. But if we end up getting our base too big or non-nucleophilic, in other words, using T-butyl, this is T-butoxide right here, the only thing it can do is an elimination reaction. And so we're going to do an E2 reaction. Okay. Notice the Tosyl group just doesn't fall off, giving you a primary carbocation. It actually has to be reacted with a good nucleophile or a strong base. Okay, questions on that? All right, so how else can we play with other ways of making these alcohols a good leaving? Well, that Paratoluene Sulfonic Acid is one way to do it, but that's not the only one, and that's the one here in the middle. Right here, we can actually use one with just a methyl group on the sulfonic acid. Okay, so that'd be methyl sulfonic acid, and we call that the mesyl group. Mesyl group right here. Or if you want to really get fancy, you can put fluorine on the methyl group there, and you have the trifluoromethyl group or the triple group. All of these are generating the same thing. They're generating sulfuric acid derivatives that are nice and stable as anions, making them good leaving groups. So in the case of having whatever your R group is your alkyl mesylate, is the one that's going to end up having whatever nucleophile you're attacking with. In this case here, again, the R is here or there. Notice the abbreviation here is the TF on this one and the MS on this one. So we have TS, TF, and MS. Okay, but they all accomplish the same thing. They're making a hydroxide a better leaving. Okay. So let's do a summary of some of these things here. We know that we can, using sulfuric acid, we can do an acid catalyzed dehydration to give us an alkene. Okay, we learned that in chapter 8. Okay, but we also can use POCl3 and pyridine. Okay, that also abstracts the oxygen and gives us our alkene. Okay. However, if we use thionyl chloride or phosphorus bromide or HX, we can get that substitution to give you the alkyl halide. Remember, HI is the only way to get to an iodine. Okay, zinc chloride and HCl is the way to get to a primary alcohol, or you can use thionyl chloride or PCl3. All of those will get you to our system. So that'll give you a a leaving group that's an iodine, a bromine, or a chlorine. So those are also good leaving groups when they're being attacked by nucleophiles, or they're also good leaving groups when they're attacked by bases. But the nucleophile is going to give us substitution. The base is going to give us elimination. Okay. Now, the last one is to use a sulfuric acid derivative, turn it into the Tosyl group, a good leaving group. And if we turn it into the Tosyl group and do a good leaving group, we can do the same thing. We can do a substitution with a good nucleophile or elimination with a good base, a non-nucleophilic base. All right. So alcohols do a lot of things. We can make ethers out of them. We can make alkenes out of them. We can make alkyl halides out of them, or double bonds again. Okay. So what if you want to run a reaction? And the reaction you need to run, you're going to use a very strong base, like an acetylide ion or something else. In this case, we're using an acetylide ion here. Okay. What's wrong with an alcohol in this case here? The OH, it has an acidic proton, right? The pKa of our alcohols is between 16 and 18. And so that's an acidic alcohol, the acidic hydrogen on there, right? The pKa of our acetylene was 25. So that means it's going to be the stronger base, and it's going to deprotonate our alcohol. And guess what? Once you deprotonate the alcohol, your acetylide ion can't act as a nucleophile. So we have to protect that OH so that it doesn't react. It doesn't have that acidic proton on it. And so this strategy is called protection, reaction, deprotection. So you're getting your alcohol so that you can run a reaction you couldn't run with it on there, and then you regenerate it after the reaction's over. So it's protection, reaction, deprotection. Okay. So turns out one of the really easy ways to do it is to take this isobutylene right here, and we're going to use it as an acid catalyzed, but we're going to use this as our nucleophile, and it's going to attach to the center carbon right here, giving us this tributyl protecting group. Okay. So the only thing we've done is remove that proton and create an ether. Okay. But we created an ether we know we can break. Okay. That's why we've done it there. So that's our protection part. Okay. Now that we have the T-butyl group in there, we can do our reaction. Again, with this, we would actually just turn to this, and then we'd end up, that would boil out of our solution. It wouldn't work at all. So what we're going to do is instead do a multi-step synthesis. The first step is sulfuric acid and then adding our isobutylene to create our T-butyl ether here. Now we have no acidic protons. Now when our deprotonated acetylene can act as a nucleophile and do an SN2 reaction to give us our new carbon-carbon bond. We're forming this carbon-carbon bond here. And then just by heating it with a little water and acid, it's going to clip off that and turn it into T-butyl alcohol. And you'll regenerate your alcohol. So, okay, questions on that? So in this case here, we're able to get a reaction on a substrate that you normally couldn't do. And alcohols are one of the most commonly protected and deprotected functionalities we have. Okay, so there's another way to do it. If we don't want to do this T-butyl ether group here, we can actually do something that's even easier to clip off. Okay, we're going to do a protection using a silyl ether, or an ether containing silicon. Okay, so this is a really common one. You can use the trimethyl, or this is a T-butyl dimethyl. It's TBSCl, because we're going to get this chloride off. This oxygen is going to come in and react with this silicon to create a new silicon-oxygen bond and generate a little HCl in there. So now we've protected it. Okay. Now, in the other case with the T-butyl, we had to heat it with water and acid to clip it off. Okay. Turns out the oxygen-silicon bond is really sensitive to fluoride ion. So all we have to do to break it off is to add a little bit of HF or a little bit of a fluoride salt. At room temperature, it just clips that bond and creates a nice strong silicon fluorine bond and regenerates your alcohol. Okay, so that means that we have a very easy way to put something on, and with that silicon ether, that silyl ether, we can actually then clip it off with very easy stuff. So sometimes you'll see it step 1, you know, this, step 2, some reactions, step 3, fluoride ion. And you know you're clipping off that silyl ether if you see fluoride ion in a multi-step reaction. Okay. So I said before that we like ethers because they're very hard, very insensitive to acids and bases. Well, you can get HI and HBr to react to cleave that. It's not easy, but you can. And so in general, what we have here is you actually end up needing 2 equivalents of HI or HBr, and you can actually remove the water. Okay. The first step is to clip the bond, creating an alkyl halide and giving you an alcohol. And then the second step is an acid catalyzed dehydration of the alcohol, or acid catalyzed substitution, to give you the second equivalent of your alkyl halide. So this is great if you have a symmetrical alkyl halide. You get 2 equivalents of alkyl halide out of it. Okay. So let's look at how we could do this right here. Ooh, this one's actually unsymmetrical. So it's going to clip here to give us our methyl bromide, and here to give us our ethyl bromide plus 1 equivalent of water. Okay. So usually this takes a lot of heat. So you have to boil it for a long time to do it. Okay. So in this case here, we're going to clip it here to give us our tertiary alkyl halide. Hey, that's one of the few tertiary alkyl halides we've had so far, right? And our primary alkyl halide. But again, 2 equivalents, and we generate 1 equivalent of water. Okay. So we've talked about some of these compounds here. Diethyl ether is a good solvent. THF is a good polar aprotic solvent. This is another one that's similar to, we've seen dioxane, but these right here, this dimethoxyethoxyethane is a very high boiling solvent, but it's an ether, so it's nice and stable, except under extreme acid conditions. And then this right here is an additive. This is methyl T-butyl ether. It's used as a gasoline additive. And so it has a weird smell. Okay, so let's take a look at the mechanism, see how it works. Well, let's see, there's only 5 things that can happen in a mechanism. Add a proton, take the proton away. So we're probably going to add a proton because we have acid. Okay, so we're going to add a proton, and now we have a protonated ether right here, which means it can leave as a neutral alcohol. Okay, so that means it can leave as a neutral alcohol, giving us our alcohol plus our carbocation right here because it left without substitution. And so we broke a bond, we protonated, and then we broke a bond. And now we're using a nucleophilic attack on an electrophile, giving us our alkyl halide. And then, well, what do we do with that alcohol? I said we got 2 equivalents of alkyl halides out of there. Well, what happens to that is we have our acid catalyzed substitution reaction to give us our iodine again. Again, we get our protonated water right here, our protonated alcohol, followed by substitution by the iodine, giving us a second equivalent of our alkyl halide. So what if you wanted the alcohol? Well, then you'd have to isolate it, make it back, get it back again with some hydroxide. All right, questions on that? Notice even in this case, this cleavage of ethers, we had to use something to make it a better leaving group. In this case, it was the acid catalyzed system. And in the case of the having the tertiary here, it can leave as a carbocation. If we were doing a secondary or a primary, it probably is a substitution reaction. But it works really well with the tertiary. All right. So where are we? Okay, great. Questions on that? So I think you have 10 new reactions to put on your reaction table if I've been counting correctly. So, okay. So now let's talk about epoxies. Okay, they have their own regioselectivity of reaction, and it's based on whether or not there's going to be acid there. But we have to make them first. Okay, and so we actually have 2 different mechanisms, 2 different ways to make this. The first one is called MCPBA, or let's see, metachloropurbenzoic acid. Okay, so let's look at that structure here. So when we make epoxies, the best way to do it is to use what we call a per acid. Okay, a per acid is a carboxylic acid with 1 extra oxygen in it. And that creates a very interesting structure here because this oxygen's partially negative and this oxygen's partially positive. Okay, that means our alkene can reach out and start grabbing at that partially positive oxygen in the per acid to generate its part. So MCPBA, metachloropurbenzoic acid. Okay. So one way we can make our ether, our epoxy, is to use base on the product of the upper chlorohydrin, something that has a leaving group. You're going to turn the oxygen into a nucleophile, and it's going to react with itself, with its other end of its chain. And when it does that, it makes that 3-membered ring here. It's an SN2 reaction. And so we kick out our halogen and we have our material. So gosh, it's a 3-membered ring. But guess what? This reaction goes really, really fast. Okay? Because it doesn't have to move anywhere to do the attack. It can just bend around and attack on itself. Turns out most intramolecular reactions that happen within the same molecule happen about 5,000 times faster. Why? In an SN2 reaction, you have to have them diffuse together and have the right energy and be in the right position, right? Well, this is an SN2 reaction, but now you have your nucleophile and it's just going to go, it's just flipping around like this, and eventually you'll get close enough to this to kick out your leaving group. And so it's just really close. It's just so approximate that the more it's going to be having more chances to close that ring. Okay. All right. The other way to do it is what we use instead, we use an alkene. And the alkene is going to be our nucleophile in this case, and reach out and grab that partially positive oxygen of the peracid, generating our epoxy compound and a regular carboxylic acid without that extra oxygen. Okay. So let's talk about that mechanism. Okay. So we're going to do a nucleophile reacting with an electrophile here. In this case here, we have 2 electrons from the pi bond reaching out and making our first bond to oxygen here. The second thing that happens is we transfer the hydrogen over here while giving up those electrons to the oxygen and breaking the oxygen-oxygen bond all at the same time. So now these electrons that were here, let me change colors. These electrons that are on the oxygen are now making the new bond over here. And the hydrogen lone pair is over here. So the alkene makes one bond with the oxygen makes the other bond with the carbon, and that's how it is made. And so it's a really fast reaction. Think about it, just everything just kind of changes partners there. Okay, so, but what this means is that it all depends, the stereochemistry depends on which side of the alkene your peracid came to. If it comes on the top, you get one isomer. If you get the top from the bottom, you might get a different isomer. Okay, cis alkenes will give a cis substituted epoxy. Okay, why? The reaction happens all at once. So whatever side your substituents on your alkene are going to be on the same side in the epoxy. Okay. So what we'll see here is, like for this right here, it's going to add across the top. But notice these are both on the same side. Our epoxy has them on the same side. Okay. Now that's if it came from the top. But if it comes from the bottom, it's going to be different, right? No, it's just going to give you a different compound. And so I mean, it'll just give you a different isomer. And so these are technically enantiomers because your chiral centers are here and here, here and here. Never seen a chiral center all bonded with the same oxygen before, but it is. There are 2 chiral centers there, and those are enantiomers. Okay, let's see. All right, so do we see how to make epoxies? So we have two ways. Halohydrin with base, and it's going to close the ring to make the ether. So that's like a Williamson ether synthesis. And the MCPBA, metachloroperbenzoic acid. Yes?
How are those enantiomers not the same molecule? Like if you rotate one 180 degrees?
Okay, so let's say you wanted to, if we were to rotate this 180 degrees, the ethyl group would be on this side, the methyl group would be on this side.
Oh, it's a methyl.
Yeah, they're on the same, they'll still be on the same side, they're coming out at us, but we'll have an ethyl and a methyl, so they're an ethyl. Okay, so now that we've made this, we make it because it's so many things we can do with it. We can do a lot of stuff with these epoxies in their system. So let's think about how we open up our epoxies, okay? So in this strained epoxy ring, you have to have the attack of the nucleophile from the bottom. The oxygen's blocking the top. So the nucleophile has to come from the bottom. Okay, so what you end up with is an anti-attack. Okay, so when you do your stereochemistry, you have to make sure you do an anti-attack. Okay, now if you have a strong nucleophile, that's a kinetic thing, right? Nucleophilicity is a kinetic thing. acids and bases are thermodynamic, right? So in a kinetic thing, you're going to want to do it fast. So you want to do it on the least substituted side because you don't want anything getting in your way. So if you have big groups there, your strong nucleophile is still going to go to the less substituted carbon. Okay, good nucleophile, less substituted carbon. However, if you use acid and a poor nucleophile, you get the other thing around. It actually gets you the more substituted side. Okay, has a different mechanism, because in this mechanism, all it is a standard SN2, where your OH, your O minus here is our leading, okay, and then eventually gets protein. So this was our nucleophile SN2, and we get on that less substituted side. Here, we're going to go through a different mechanism, and therefore we're actually going to end up with the OH on the more substituted side. Okay. So in our mechanism, we might be looking for maybe a partially positive charge, because that way the more substituted side is going to have more of that partially positive charge, because tertiary carbocation is more stable. Okay, so let's see what happens right here. So if we do it with just a straight nucleophile, a good nucleophile, so this has a negative charge, it's sulfur, it's just going to do an attack on the less substituted side because it's steric. See, over here it has to come up with in between these two methyl groups. Remember, these methyl groups have hydrogens on them too. They take up more room than they look. Hydrogen, hydrogen, hydrogen. So it's going to come in and attack the less sterically hindered side, okay, giving us our kinetic product, or our less substituted carbon getting the nucleophile. Okay, so that means all of our nucleophiles that have already have negative charges on them, and nitrogen. Remember I said epoxies are used in things, and you have the two parts, the stinky ones and amine. It doesn't even have to be deprotonated. It's a good enough nucleophile by itself. Okay, and so they'll all do a SN2 attack on the less substituted side. Okay, does that make sense? It's going to happen fast. You want to do it on the less substituted side. However, if you change up the mechanism or change up the thing, so here we're going to add acid. Okay, so if you see an epoxy with acid, you've just changed the mechanism. Okay, in this case here, what we're going to do first is we're going to protonate the oxygen here. It's the most electronegative atom. It has lone pairs. We're going to protonate the oxygen, giving us this oxonium cation. Okay, this looks familiar, right? Didn't we have a similar state when we had our bromonium cation right there? And didn't we have regioselectivity because of that? So in this case here, or even like in the oxymercurization, demercurization, the mercury went on one and it had a longer bond for the more substituted side. Okay, so what's going to happen here is we're going to do that same kind of thing, that same kind of transition state, where the more stable cation is the more substituted side is going to have a bigger portion of that partially positive charge, and therefore it's going to be attacked selectively on that side. And since this is the more stable transition state, it's the lower energy transition state, and therefore it's the faster reaction. And so it gives us our substitution at the more substituted side of the product. Now, doesn't mean you can't attack the other side. You might get a little of it, but again, it's a much slower reaction, and so you're going to see very, very little of it. So in this case, you would only have to draw one product for this, the more substituted one. Okay. And then, you know, whatever your final product depends on what you're reacting with. If you're attacking it with hydroxide, you're going to get a diol. If you're attacking it with a halide, you're going to get a halohydrin. If you're attacking it with an ether or something, it's going to do something else. Okay. All right. So let's see. Does that mechanism make sense? Right? The acid changed the mechanism, turned it into a more. So we did figure out that we could make dihydroxy compounds in the last thing by using two different reagents. We can use potassium permanganate cold or osmium tetroxide. Okay, and this is cold. Right here. Okay, but they both made cis diols. They both made cis diols because they added both oxygens across the double bond at the same time, and then we had to reduce off or take off the metal ester that was there. Okay, but now that we have an epoxy, and we know we can open our epoxy with a nucleophile, now we have an opportunity to get an anti or a trans diol. This is our first time to get a trans diol. We got our cis diols last chapter, and here we're going to get a trans diol. So how do we do that? Well, it's a kind of a couple step reaction here. Instead of just being one step, what we're going to have to do is we're going to have to make our epoxy using our per acid. See how there's 3 oxygens in there? It says RCRO3. That's a per acid. If there's O2, it would be a carboxylic acid. And that's going to give us our epoxy right here. Now, the reason we're getting our trans diol here is because when our epoxy is there, the nucleophile has to attack from the bottom side. So it has to attack from the bottom side, just like when we had the other bromonium thing, where the anti-addition from the other bromine. And so that gives us our trans diol. Okay. So that's a good, nice way to do it. And again, we can do that with just a little bit of protonated water. And we're doing that same thing. We're going to change that mechanism. And we're going to protonate our ether first. Then we're going to have attack by our poor nucleophile. Here we don't have a choice. It's going to be the secondary on both sides, so it doesn't matter. And it'll give that. So if it attacked on the other side, it would give the different enantiomer, but it would still give you a trans diol. It's going to be a 1,2 diol. Okay. Oh, and then, yeah, making it into an ether there. Okay. All right. Let's still translate. All right. And that is the end of chapter 11. So now you have every reaction you need. Okay. On Wednesday, I'm going to do a retrosynthetic in-class thing. We're going to take the quiz on that, and then on next Monday, we will start with our full review, starting with chapter 1. And we'll have 2 classes and 1 more quiz. Don't forget to turn in your take-home quiz. Don't forget to turn in your take-home quiz. That's going to be the easiest 9 points you'll get.
Let's do Wednesday.
Yes, at midnight. Wednesday at midnight. All right. Any questions now already? Have you already started studying for the ACS?
Are you gonna have time to review like all the chapters?
Yes. Yeah, I will be reviewing all the chapters.
The quiz is on chapter 11.
The quiz on Wednesday is on chapter 10. The quiz next week will be on chapter 11.
Which was the take home? What was that?
And what?
Which was the take home quiz? Or that's
The one, it's on Canvas. You download it.
yeah,
it's several pages.
Which chapter is the take home quiz?
Oh, the take-home quiz is over 8, 9, 10, 11.
Okay.
Yeah, and they're separated out by chapter, so you'll know which chapter to go to. But there's a really good exercise on there. It's what I call the scatter, which is you start with the same material and you have a whole bunch of different reagents. See, that's I think that's going to be good. The retrosynthetic thing we're going to do on Wednesday, we're actually going to do that thing where you have it going forward, going backwards, and in the middle for a bunch of different steps. And I'm going to cover all the reactions in that. And so then we're going to say, okay, I'm going to take a reaction from chapter 6 and a reaction from chapter 10 and a reaction from chapter 11, and we're going to put them all in different orders and go from one functional group to the next functional group to the next functional group, and then talk about where it might show up in IR or NMR, kind of tying everything together. Now, the ACS exam, if you haven't already got a study book, go get one. It'll do this and next semester. We're taking the first term version of it. There are 70 questions. Average raw score is about 50. So that's not a problem. I did have actually one of my students who was in my Gen Chem class, music major, got a 69 raw score out of 70. He did not change his major. It's still in his. Anyway,
Wait, it's only 7 questions.
70 questions.
7. Oh,
No, 70 questions. Yeah, part A, part Z. Have a lot. So it's going to be multiple choice. I'm going to give you one of the big scantrons, and you're going to have to fill in your name and put on your. Oh, by the way, if you don't have an ID, you must bring an ID. I have to see an ID, and you can't. I have to have all the scratch paper and everything back.
You will curve the Ross board.
Yeah, depends. Yes, I'll be curving the Ross board. It'll be a simple curve though, because that's how we do it. But we have one more exam, 2 more quizzes, plus the stay-home quiz. So we've got some scores here.
Do you do the replacement final like post-grade?
No, the final's the final. It tells me that how much you've learned. So there's no replacements. I mean, I do drop 3 quizzes, and I've given you a total of 12. Well, yeah, because there's a total of 12 quizzes. I take the top 9. So you do get 3 drop quizzes, so that's good. And everything's been curved up to now, and you have 1 more exam. And the exam's just gonna focus on 8, 9, 10, and 11. So, all right. So, thank you very much. I'm gonna go ahead and stop recording. Stop sharing. When is exam 3? It's the last day before our last day of class. Let me pull it up on Chrome here, Google Chrome. It's on May 2nd. May 2nd. Okay. All right. All right. Let me stop recording. Sorry.